Welcome back, guys. With me is Rikard Hjort, Senior Formal Verification Engineer at Runtime Verification. He's based in Berlin. Hi, Rikard.
Hey.
So Rikard is going to talk about K framework for smart contract formal verification. We are big fans here at Ethworks of formal verification. So I'm excited for that. Yeah, without further ado, Rikard, the stage is yours.
Okay, thank you guys. So I'm Rikard, I live in Berlin. I'm Swedish. I joined Runtime Verification a little over a year ago after having done my master's thesis there and so on. And I joined mostly because I really want to work in blockchain. But I also have this affinity for math and logic and the field called formal methods, which has traditionally been slightly academic, but with the advent of smart contracts, it's become more of a practically applied field, and runtime verification is one of the, well, perhaps a market leader in doing formal verification or using formal methods for blockchain applications. But I'll get into more what we do in a little bit. Let's see. Roughly the topics I want to cover. If you want to derail me with questions, feel free. I think this will take slightly less than an hour. So feel free to drop any questions on the way. I'm going to cover a bit what formal verification is, sort of what kind of blockchain vulnerabilities there are. I don't know really what level of security awareness the audience has here, but I'll explain a little bit of the basics of what kind of security holes you need to be looking for when you're building smart contracts. I want to show you a bit of the K framework, which is the open source tool that we use to verify contracts, verify blockchain protocols, layer ones, DeFi protocols, and so on. And also show you a little bit of what kind of tools we're building using this framework. So Runtime Verification is a startup aimed at using formal methods to perform security audits, mostly on virtual machines, smart contracts, but also on blockchains, layer ones. And I mean, our goal is to improve the safety and reliability of smart contracts because, you know, once they're deployed, they might handle millions or billions of dollars in worth, and well, hacks are scary, and it's really hard to build the foundation of a new financial system if it feels really wobbly and it's prone to simple attacks. So we do formal verification. I'm not sure everyone knows exactly what that means. It's a word you might hear thrown around a lot. It has a few specific meanings, and it has a few wider meanings that you will hear used, especially in blockchain space. But in essence, it's a process of checking. Okay, so this is a bit academic speak, but to be precise, it's a process of checking if a design satisfies system's requirements. So basically what you do is you use some sort of formalism, which is just another word for math, really. So you specify your system in some sort of mathematical way, and then you use mathematical techniques to prove that your system behaves according to its specifications. So you can think of it as, well, you know, if you're doing quality assurance, you've constructed a system, you want to push it live, you want to deploy your new DeFi protocol or your smart contract. What you might do is you might think very closely about, like, how should this system behave under various different circumstances, and then you write a whole lot of tests for it. You try to find all the edge cases and so on. The benefit of formal verification is that, well, you're using math. So instead of saying, well, my function behaves correctly for this specific input when I choose this specific integer, like 42, right? Instead, you say, well, my contract behaves correctly on all possible inputs. So you're covering all the scenarios, you can detect all the corner cases, and you can catch a lot of common design errors. It's also pretty good because if you want to prove that your system behaves according to a specification, you need to be really exact about your specification. You will often find that you have left some things underspecified. Something we found when we implemented the EVM, like the Jello Paper, was that we found several places where the Jello Paper didn't exactly specify how to perform certain or to act in certain situations. So, but as you're writing a formalism, you need to really start thinking about what kind of you need to make sure you actually have an exact description of what you want to prove. I don't know if any of you are familiar with property-based testing, like a quick check, but it's sort of the same idea. You write a property, you say something, well, the system should always behave in this specific way. This function should always have outputs that look like this. Like classic example, if you reverse a list and then reverse it again, you get back the same list. That's a property. And the way property-based testing works is that it generates a lot of random inputs, or, well, pseudo-random. It tries to construct a lot of different outputs in a random fashion or a stochastic fashion and prove and show that the property holds for each of them. This is sort of the same thing. You write the same kind of properties, but instead of using random inputs, you use symbolic inputs that can stand in for any value, and you prove that it still holds your property. So there's plenty of different verification use cases. Traditionally, formal verification has been really important for embedded systems. It has a long history in, for example, hardware design, because, well, you're building this really advanced chip that's going to go in a really expensive machine, and you don't want to encounter the situation that Intel did a few decades back when it had an issue in one of its floating point instructions and had to recall all its processors from that line. So in hardware design, formal verification is often used to just make sure that, you know, your design is correct before you send it off to the factory and manufacture 100,000 of these chips. It also has a long history in automotive, aerospace, nuclear, robotics, public transport, automation, really anywhere where there is software that really puts people's lives at stake, or that puts, you know, a lot of physical collateral at stake. Like, for example, if you're designing a space shuttle, then you want to make sure you don't have errors. It's really hard to like formally verify the entirety of the system, but you want to make sure that some certain key functions never screw up, right? Same thing if you're designing a self-steering system or like an adaptive car system, and you want to make sure it doesn't accidentally have some weird corner case where it will just, you know, spin the wheel and throw you off the road or something. But of course, like in later years, blockchain has emerged as a really important use case for formal verification. And one reason for that is, well, of course, like you're dealing with a lot of collateral, you're dealing with a lot of money. These systems are really valuable, and if there's something wrong somewhere, a lot of money could be at stake. So you can use blockchain for layer 1 protocol design, or sorry, you can use formal verification to analyze a layer 1 protocol design, like does this protocol behave the way you expect to? Same for layer 2. Smart contracts is a big one, like verifying that your smart contracts behave as you expect them. You can also use it for tokenomics, like modeling a system and showing that, you know, it doesn't have any weird logic holes or feedback loops that you want to avoid. And of course, DeFi systems. You can model how a few different modules interact with each other and make sure that, you know, there's no way that one part of the system can ruin the rest or something. So, I mean, usually at this point, I'm not seeing any questions yet, but usually at this point is when people start asking, okay, why, that sounds great, let's do it. Why don't we just formally verify everything and just be sure? And I mean, there are a few barriers to entry. It's not that easy or cheap to do formal verification. So, well, when a company or a team or a developer or just someone wants to formally verify something in their project or just a piece of code, it's common to face a few different obstacles. So, on average, unless you've done this, it's really hard to make an estimate of how long it will take to formally verify code. Like, just because the system feels simple in your head or looks simple on paper doesn't mean it's actually going to be simple to verify. You can sort of use a heuristic based on the length of the code. Like, the longer the code, the longer it's going to take to verify. But all in all, it's harder than one might think. A big reason for that is like, well, you're not just trying to convince a person. Like, you're not writing a mathematical proof just to convince a person. That's something you can do. That's something we do, definitely. We call it manual formal verification, where you construct a paper proof that's convincing enough that the properties you want to prove hold. But mostly, and the thing we want to do as much as possible is to use mechanized proofs, which means that you construct a proof in such a way that a machine can check it. And that means you have to convince the machine that your proof is correct, which is a lot harder than convincing a person, because you can't really hand wave because the computer doesn't understand hand waving. You need to be really explicit about everything. Another big barrier to entry is like you may need to do a lot of upfront modeling. You need to really think about how your system fits together. Different designs are can have like different levels of amenability to verification. Of course, it's hard to find qualified talent. Like, that's what I said when I came into the space. I started like getting into blockchain in 2017. I started getting really into logic and like computer science, like hard computer science, in like 2018. And I realized that, well, there's so much cool stuff going on in like that single corridor at my university, and they're building all this amazing tech, or they're building really amazing theories, and they're doing cool stuff, but it's not really getting applied outside of the system. It's a pretty small academic field, or has been historically. So it's still pretty hard to find qualified talent to do formal verification, especially like if you want to do both blockchain and formal verification. Like that's a really, really small overlap, or it used to be. It's really growing. I see a lot of more people getting interested in this. I talk to students all the time who are saying like, well, that formal verification and blockchain seems like such a cool match. So a lot of people who get off on the same nerdy stuff that I do can really see like this is something that they want to focus on. But of course, you also need senior people, and it's hard to find qualified talent. And then, I mean, all this kind of comes together into saying formal verification is not cheap. It's not something you just throw on at the end of your project. I mean, you could do, because like formal verification has some similarities to testing. There is something that is like full formal verification. You completely verify your systems in its entirety of inputs. But usually what you do is you specify a few key properties and make sure those hold. But of course, like you can scale this to really small, like you really only verify a single property of a single function into you're verifying a lot of big properties of the entire system. All of those really classify as formal verification. So if you see some project that says, well, we formally verified something, that's great. But it's usually good to like ask what they formally verified. It's the same as audits. Like we did an audit. An audit can take, there are half-day audits and there are month-long audits, right? But overall, formal verification is more expensive than many other types of audits because it's so very exact. And yeah, it takes a long time to do. Let's see, I have a question from Thomas. Very interesting presentation, thanks. Well, thank you. Do you want to verify all protocol or only some parts? If so, which one? Yeah, that's kind of what it boils down to, and that's something we will often discuss in together with the team building the protocol, what are the most important properties to verify? Like if you are, I mean, for like a very simple example, like you probably don't verify the UI a lot, like the Web3 implementation. So instead you focus on verifying the smart contracts. Well, I mean, you could verify the UI, and it might be really important to like make sure that it doesn't show the wrong things. But usually, people are feel kind of safe with the fact that like, okay, as long as the smart contracts behave the way you want, then you're good. But even there, like depending, like if you have big money Legos with thousands of lines of code in each smart contract, it's kind of hard to specify the exact behavior of the entire system. You might like skip over view functions, or you might kind of hand wave away specific ways that contracts interact with each other. Usually, I mean, it's usually a good start to just start with like functional specifications, saying like, well, here's a token swap function, right, in a DEX, decentralized exchange, where you just specify, okay, if this transaction goes through, then you will have at least this much money. Like, you know, showing like if you're swapping on Uniswap or SushiSwap or any DEX, you will see that the function call has like a minimum amount, like a slippage factor, and you might want to show like simply, well, you know, if you don't meet that slippage factor, then you know your contract or your swap will fail. And once you have those, if you still want to verify more, then you can kind of start combining different functional specs with each other and start showing that, well, even if you do first a swap and then add a liquidity, then remove liquidity and like another swap and so on, no matter how you arrange things, certain safety properties are always met. Like, you know, the K constant in a K equals X times Y DEX isn't violated and so on. Yeah, hope that answers your question, Thomas. And I mean, I should add also, like, you sometimes do verification where we are looking at like the entire instead of verifying the exact code, you might want to create a model of the system and verify that model. So now you're not verifying the exact smart contracts that are deployed. Instead, you say, well, they behave in this sort of simplified fashion, and then you show that leads to specific properties. Kind of depends on what you want, kind of depends on what kind of testing is already in place, but usually high-level protocol verification is usually a good idea, and low-level functional code specification is usually a good idea. And then you can kind of start figuring out, based on those, what more things you will want to verify. In the end, it's all about making sure that you find as many security holes as possible, as quickly as possible. So it's a bit of an art form. Or, you know, in as much as engineering is an art form, right? It's engineering, trying to figure out the best way to do this. So when it comes to mitigating blockchain vulnerabilities, what kind of things are you aiming for? So the reason that blockchain verification or formal verification is interesting for blockchain is basically the same reasons that it's very attractive to attack smart contracts. They're easier to verify than a space shuttle software because it's open source and the code is pretty small, and it's worth it because there's a lot of funds in the contract. Of course, that's also exactly what makes it attractive to attack. You have open sourced, easy to access smart contracts. The code is pretty short. You can usually sit for a day or two or even less analyzing a few smart contracts and trying to find a security hole in it. And of course, there's a lot of money to be made if you do it. There are a few different ways that you can attack a smart contract. The ones that we focus on are sort of the on-chain ones. So you have design vulnerabilities, basically the way holes in the protocol or the assumptions about how things will interact with each other, and code vulnerabilities, like, if there's a little bug, like what you usually call a bug. If there's a bug in the code which will let you do something that is obviously unintended, that's a code vulnerability. But of course, like, there are other aspects to security, like if you have a DeFi project that is protected by an admin or by a DAO, then social engineering can be an aspect, trying to figure out ways to attack the system by attacking the people controlling it. There's also, of course, like legal pressure, phishing, but these are all kind of external to the blockchain, and of course, you get into territories where you can't really mathematize how things should behave. So when you're dealing with formal verification, what runtime verification does is that we focus on design vulnerabilities and code vulnerabilities, basically the pure code, the pure systems aspects of security. So design vulnerabilities, like I said, it's basically flaws in business logic, like economic attacks, flash loan attacks, and so on. Code vulnerabilities are, the coder didn't really know how send instruction in EVM or in Solidity works, or what kind of edge case it had, and therefore they introduced a bug, and now the contract can be locked or sabotaged or something. It's an example of a code vulnerability. So I mean, if you want an example for a design vulnerability, then you can think of like, okay, so it's if you have a layer 1 protocol for a blockchain called PantsCoin, and attacker figures out that they can revert 47 blocks because they have found out that the protocol is implemented in such a way that you really only need to control 3% of the network, validators under certain conditions, and then the attacker double spends a lot. Or in a smart contract example, say you have Fennel tokens. They are on exchange called AnisSwap, and a mechanism introduced by the AnisSwap devs to promote liquidity was over-leveraged in illiquid markets to drain Fennel swaps through an Oracle attack that screwed up the prices. Whereas a code vulnerability would be more like an attacker figures out that a really popular PantsCoin client, let's say it's called PantsBot, will confirm any transactions submitted to the node during the time the client is handshaking new peers over the network, and then you can start double spending. Smart contracts example would be, so a lot like DeFi projects often, there's a launch deadline, people are anticipating it, like hammering them in the Telegram channels, and they do a last minute refactor. So let's say that it's AnisSwap last minute refactor, code missed a case where safe math should have been used. Well, Solidity 8 means you don't need to use safe math anymore, but you used to have to do that before. And now, an attacker can withdraw more Fennel tokens than allowed because they can cause an overflow. So the way you tackle design vulnerabilities and code vulnerabilities are kind of similar. Some difference. Basically, the lowest level of assurance that you need for design vulnerabilities is to make sure you have a good specification. Like if you can't write down what your system is supposed to do, there's a good chance you haven't really thought it through. Then you can submit it, like once you have a specification, you can submit your design to an audit, and you can have auditors trying to like really massage the system and poke it and see if they can break it. If you want to be have higher assurance, you can start doing modeling, some random testing, trying to see if there's any way to break the system once you have a mechanized version of it. And then you have verification, which is essentially what runtime verification specializes in. We also do modeling and audit, of course, but our claim to fame is that we're pretty good at verification. And if we have a model, we might be able to prove that it has specific safety properties. And when it comes to code vulnerabilities, what you would do is start with testing, right? Again, like here you have an implicit assumption of a specification for what the code should do, but you start testing it, you write tests, the tests kind of turn into a specification, and then you follow the same pipeline. So you contact an audit firm like Runtime Verification, we look at your test, we audit your code, we see if there's any obvious issues. Then there's like static analysis, trying to use as much automated process as possible to look for typical bugs like reentrancy or so on. And in the end, verification, like, okay, can we prove that your code behaves the way you expect it to, and there's no weird edge cases. I was kind of hoping I could get a show of hands, but I don't think I can. Basically, well, here's an example of a reentrancy issue. So I don't know how familiar you guys are with code auditing or looking for typical issues. I hope a lot of you have at least heard of reentrancy. Here's just an example of what reentrancy could look like. This contract has a bug in it, or has a reentrancy vulnerability. It's a really simple contract. It's a store, so you can, or it's a storage, so you can send any amount of ether into it, and then every week you can withdraw up to 1 ether. So you can make at most 1 withdrawal a week, and at that time you can withdraw as most 1 ether. So, you can imagine this being part of like a larger DAO or something where you want to have some sort of vesting like schedule. It's really simple. It just says like, well, the withdrawal limit is 1 ether. The last, for every user, it can see what it stores what the last time they withdrew was. They store each user's balance. You deposit to the contract. It's just going to increment your balance. And then when you do a withdrawal, what you do is you, I don't remember which version of Solidity this is, so the syntax might be out of date, but well, you basically say that, you have to have a balance higher than the amount you want to withdraw. It has to be less than 1 ether that you're withdrawing, and it has to have at least 1 week has to have gone by since you last withdrew. And then you send back to the account withdrawing using MSG sender, the call with a specific amount. You check that the send finishes correctly, then you decrease their amount, and you store that, okay, they accessed their funds today, which means that they will have to wait a week. So you have Alice saying, okay, cool, I don't want to spend my ether because they're ultrasound money, so I want to put them away so I don't accidentally start spending them. So Alice puts in 2 ether, Bob puts in 2 ether, and now there's 6 ether in the contract. Alice's balance is 2, Bob's is 4. Can anyone see the issue? What the vulnerability is? I'll give you guys a few seconds to think about it. Okay, so the issue is this line. Or rather, it's the way that this line relates to this line. So basically, you don't decrease the amount of Alice before you send her, or sorry, you don't decrease the amount of the account withdrawing until after you've done this send. And the reason that's dangerous is because, well, this works fine if all the people withdrawing are end user accounts, so they can do a single transaction. But of course, there are both end user accounts and there's also contracts on chain. So whoever's calling the code, the Ether store, could be a contract. And what happens when you send Ether to a contract? Well, you invoke its fallback function or its receive function, depending on what version of Solidity you're using. So an attacker, Eve, can deploy a contract and basically have that contract deposit 1 Ether into the Ether store. So there's some other function here that says, okay, we're going to deposit 1 Ether into the Ether store. Now the balance of this contract, the attacker contract, is 1. That means that the Eve can now call the fallback function. So the fallback function basically says it's going to check the amount of Ether in the contract, in the Ether store contract, and it's going to call withdraw as long as there is more Ether in the contract. And of course, the problem with that for the Ether store is that, well, the withdraw function is going to get called, the balance is going to get checked, it's going to be 1 Ether, that's fine. The withdrawal limit is met, so she's withdrawing 1 Ether, she has 1 Ether in her account, that's fine. She hasn't done any withdrawals before, so, pass this check. Then it's going to send the Ether to this account. But sending that Ether invokes this fallback function. And then the fallback function can just call withdraw again. And since none of these variables have been updated, everything still works the same way. So you keep going into, you're hitting this line, you're getting more Ether, more Ether, more Ether, more Ether, and so on. And until the fallback function doesn't invoke this if case, and it's done. Now it's withdrawn 7 Ether from the contract. And then as the call stack unwinds, of course, like all these function calls have to end, so you will pass this line a bunch of times. This line will just decrease this attacker contract's amount a bunch of times. It will be -7. But that's fine because the attacker already has gone off with all the Ether and the call will succeed, and that's a reentrancy attack. So in Solidity 8, for example, this couldn't happen because, or this reentrancy attack wouldn't work simply because this would underflow. And in Solidity 8, underflows throw by default. So that's smart contract. Small errors have expensive consequences. So one really common way that people try to deal with this is that they become super defensive and they want to put a lot of requires clauses. They want to check that everything works. They get really paranoid and want to make sure that there's no, they'd rather fail than do something bad, which is good in theory, but it's also not completely safe. And my favorite example of that is grieving contracts. Here's a simple one. Again, you can think of it as part of a DAO or something more complex, but basically this is a simple contract that you can take over. So first it's owned by the current staker is the 0 address and there's no stake in the contract. And whenever someone calls the takeover function with more Ether than was previously in the contract, or was the previous current stake, they become the new staker. So if I call in here with 1 Ether, then, well, the value of my transaction is larger than the current stake, which is 0. The 0 Ether gets sent to the 0 address. That's going to be successful. So here's this little defensive thing. The coder here has decided, okay, we need to make sure that the call succeeds, and if it doesn't, we should throw. So there's no there's no takeover happening unless the previous staker gets their money back. And then, the current staker is updated and the current staker is updated.
According to Wikipedia, the happening is a performance, event, or situation.
I have no idea why Google started talking to me. That's scary. So, do you see the issue with this? The issue is, what if this can never succeed? What if it's never possible to send the ether to the current staker? The way that attack works is that, again, Eve would deploy a contract with a really expensive fallback function. She'd have some function in that contract that lets it take over the control me contract, this one, sending as many ether as necessary. But since the current staker then would be a contract with a really expensive fallback function, this wouldn't work because send by default only sends long 21,000 gas. So 21,000 gas isn't really enough to do anything more than just some logging or emitting an event. So the fallback function will always fail. It would always have an out of gas exception, which means that the send would return false and you'd throw. So what's happened now is that you have a current staker that can never receive her stake back. And since we were really defensive about making sure that the current staker always gets their stake back, this contract is now griefing. Like, it's stuck. It's a denial of service. It can never make any progress from here. This function can never succeed, and we're kind of locked in a situation that we didn't want. There are other way more subtle versions of grieving contracts. For example, when you try to be defensive and you have a smart contract creating another smart contract, and it just checks that the new created smart contract has a balance of 0, because it's just like a little defensive thinking that it's an invariant that should always hold, is what the programmer is thinking. The problem is that there are certain conditions under which you can send ether to an address that doesn't exist. Well, you can always send ether to an address that doesn't exist, but when a contract creates a new smart contract, you can actually figure out what the new address is going to be. And you can send ether to that address preemptively. So, I mean, that was a grieving wallet error that I don't think caused any issues in the end. It was caught before anyone attacked it. But my point here is that, well, you need to check your assumptions. That's one important thing. Another thing is you can't, if you're not defensive enough, you might introduce bugs. But if you're too defensive, you might also introduce bugs. So there's really no way around it other than being really, really careful and checking all your assumptions and doing audits and hopefully verifying the correctness of your contract. I mean, that all sounds great. Of course, do more and do better security auditing. But I want to tell you a bit about how we do it in practice. And the way we do it is we use the K framework, which is an open source tool that was developed, or it's mostly being maintained by Runtime Verification. And we are the main users of it. Of course, anyone's free to use it. There's a lot of projects using the K framework for all kinds of things. But it's what we use. And it's actually a programming language framework. So the original idea of K is that, well, it's annoying that for every programming language you have to implement an interpreter, compiler. If you want to do model checking, you need to implement a model checker. All these all these engines, all the tools, you need to build them again for every language. And that's probably fine for C and Java and JavaScript. But even like when you come to something that's not, like Solidity doesn't have nearly as many users as JavaScript or Java, and Ethereum doesn't have nearly as many users. And new blockchain languages don't have that many users. So you might have to spend a lot of time, if you want good tooling, you need to spend a lot of time building those tools again for your new language. Which is kind of annoying, because like really, when you create a new language, you know what it's supposed to do. It has a specific behavior. You should be able to just derive all the tools. Like you should be able to derive a compiler, an interpreter, a verifier, symbolic execution engine, just from a single implementation of the language. That might sound weird, but it isn't, because like really a programming language is just a mathematical definition of what a computer is supposed to do. And that definition is really enough to figure out what all the other tools should be doing. That's the idea behind the K framework. So the idea is you can develop each language tool once, which means you teach the K framework how to derive this tool, and then you just implement language in K, and now you have all the tools you need, or all the tools. So we have one model, all the tooling. And the way it works is that K is an operational semantics framework. That means that you specify your language in this formalism. It's called operational semantics. We have a rewrite-based operational semantics. Don't worry too much about it if that doesn't sound familiar. It's just a way of saying, like, here's how you specify your language. And it's pretty similar to like a functional programming language. So it's not that hairy. So you specify your language or semantics in the K modeling language, and the K compiler just derives a bunch of tools for you. We have two different backends. We have an LLVM backend, which is used for concrete execution, so you get a really fast interpreter. And we have a Haskell backend for symbolic execution, which is what we use when we verify or prove things. So the prover is based on what's called reachability reasoning. So basically saying that whenever you write a specification saying, here's what I want, if I start in a specific state, I always want to reach this other state. And we say that the proof succeeds if you can show that whenever you start in this state, you will eventually reach another state, which is the one you want. So it's only based on this operational semantics, so it doesn't depend on the language. Like you don't have separate provers for C and Java and EVM. Instead, what you do is you give the prover both the EVM specification and the specific thing you want to prove, and it works from there. So the nice thing about that is, like, usually if you want to do proving for a language, what you need to do is, well, first you develop the language, like maybe in C++ or Go or something, and then you have to axiomatize it. Basically, you have to turn it into math so that you can reason about it and give that to another tool. But now, how do you know that the way you axiomatize your language, the way you specify it in math, actually corresponds to your Go or C++ implementation? The good thing about K is we can use the same operational semantics engine, the same definition of the language, to both do the formal verification, but also run the VM. So you can have it in your blockchain node, or you can just run all the conformance tests against the K concrete implementation, and then be pretty sure that your axiomatization, the thing you use to do proving, is also correct. So you can summarize it as run what you prove and prove what you run. So don't have two different models and, running one and then use the other one to do proving, if you can avoid it. So just examples of what we can do with K. One thing you could check out, it's really nice, is the Jello paper. Let's see, can you actually see it? Yeah. So I don't know if you're familiar with the Yellow paper. That's the specification of EVM. But the Jello paper is also a specification of the EVM, but written in K. So it's just, if you're curious about what the EVM does, you can have a look at the Jello paper, I think it looks a lot nicer than the mathematical notation in the Jello in the Yellow paper, because it looks a lot more like code. It takes a little while to learn to read this, but basically you can think of it as a functional programming language. So most programmers should feel at least somewhat familiar with this after, just a little bit of diving into it. So for example, if we encounter what's called a push call stack operation at what's called the K cell, then we get rid of it and we update the call stack and we read the call state. So just quick look at what K looks like. The Ksemantics of the Ethereum virtual machine, the KVM, is really cool. It's the first full formalization of the EVM, or the mechanized formalization of EVM, like implemented in computer language. So it passes the same conformance test suite as all the other clients, but you also have this symbolic execution, so you can do verification, which means that KVM has been sort of the primary tool for doing verification of Ethereum smart contracts. You can do standalone proofs. So like you can take an ERC20 tool, ERC20 implementation and verify that the transfer function behaves exactly the way it should. You can do lightweight symbolic analysis based on audits, lightweight symbolic analysis based audits. So you kind of run the functions with symbolic inputs and kind of see what you get. And then you just kind of reason about it on paper to make sure that that looks like what you expect. You can do full verification. We did that for the ETH2 deposit contract, for example. I found a Viper compiler bug, which could have been very, very bad for some people's 32 Ether. And you can do kind of this like large scale proving, like the multi-collateral DAI system has a verification. It's largely verified in K, and it's a total of 1,011 proofs, and they kind of work together. So you can prove smaller claims and use it to prove bigger claims and so on. That's sort of what we do, like at a high level. Is sort of the expert works, but we also try to build tools based on K that can do more automatically, that doesn't require as much expertise, but can still provide value for coders and smart contract implementers. So like I said, KVM is our most mature blockchain semantics, probably one of the most mature blockchain semantics. And we have a bunch of tools for it. So Firefly, for example, is something you can plug into your ID. You can replace Ganache with Firefly and then run your tools using KVM, run your tests using KVM, and Firefly kind of can give you a code coverage report and a bunch of other things, and more coming. We have a token verifier that's sort of in prototype. So you can upload an ERC20 tool, ERC20 implementation, and just get a proof, or you can get a proof that it behaves the way it should, that it doesn't. There's no edge cases in your transfer function, for example, or it can point them out. Usually, might require a little bit of massaging, but the point is that it should be pretty straightforward for someone to use. Of course, we also have semantics for several other blockchain languages. One of the good things about K is like when there's a new blockchain coming out and a new smart contract language, we can pretty quickly get up and running because we can implement it in K and then start doing verification and also deriving tools. So K Yellow for Cardano, K Mikkelsen for Tesos, K Wasm for Polkadot and Elrond, K Teal and K Algo Clarity for Algorand. More coming, yeah. We're just always developing new K semantics. Firefly, like I said, it's a suite of tools to help smart contract developers. Basically, you plug it in instead of Ganache, and you can run your regular tests, and now you can get special help, like generate new tests or identify testing coverage holes, because it will tell you which parts you have covered. It would not only tell you which lines of code you have covered, but also if you covered all the behaviors, like have for an addition operation, have you covered both the case when it underflows and when it doesn't underflow or overflow? So there's a few different tiers to the tools that Firefly gives you. So there's the ones that require no user intervention, like the test runner. You just plug in Firefly instead of your usual test runner. Now all your tests run on Firefly. You get test coverage, black box random testing. Mutation testing is coming. That's sort of when you mess a bit with the inputs and try to figure out if you can mess with the inputs in such a way that your tests still pass even though they shouldn't. There's some things that require a little bit more intervention, like random property testing. You have to start writing properties. You can do runtime monitoring, which means you're looking for variants being violated while your tests run. And more advanced features that require a bit more expertise, but also give you a lot more assurance, like assertion violation checking, bounded model checking, symbolic property testing. Integrates with Truffle, Hardhat, and DAppTools. And then there's the other tool I mentioned, which is the ERC20 tool. It's prototype right now, but basically what you do is you upload your ERC20 constructor bytecode. You can link to the Solidity code, so then you can see your Solidity code side by side. You just submit the bytecode. Tool reports back either yes, it's compliant, or no, this behavior is off. Can also report like, well, I couldn't really figure this out because there's this edge case where I can't really tell what would happen. But then you as a coder can reason about it. There's a demo over at ERC20 Firefly blockchain, which will show you how it works. If anyone's interested, if someone watching this on video, you can screenshot this, you can pause the video. Here's the steps to follow with the ERC20 tool. FYI, still in prototype. If you want to use it, please do. Come to our Discord and ask us questions. And the tool actually takes a while to run. Well, because it's really testing everything, every possibility. So it could take 24 to 48 hours to get a report back. The report looks kind of like this. You can check each case, each test case. So for example, like approve, there's a report that shows like, well, approve always behaves correctly. For transfer, you run a few different symbolic tests. One is that transfer should fail under specific conditions, and one is that it should always succeed under specific conditions. And if you open these, then you will be shown if it worked, what broke, what didn't broke. If it broke, and if so, what broke? What was the issue? What edge cases have you not covered? That's really all I have. I just want to say we're hiring. It's always hard to find good talent, so we are definitely looking for people who can help us secure the blockchain, secure Ethereum, secure other blockchains. Smart contract auditors. If you are a great Solidity dev and very security minded, or you've done smart contract auditors before, please get in touch. There's always people needing audits, and we are looking for auditors. Haskell developers, like if you're a Haskell whiz, let us know. Compiler engineers, and we're also open to internships. So if you are studying currently, or you're doing a PhD or a master's or just an undergrad, and you're really interested in blockchain and formal methods, then send us your resume and cover letter. Yeah, that's about it. And go to runtimeverification.com to read more about these. We're a great little team. I mean, my work kind of does look like this. I have my little math math bookshelf and working from home with my dog. It's not going to end when Corona ends. We're a remote team. We're distributed all over the world. So, yeah. Thank you.
Thanks a lot. That workplace looks very comfy. Yeah, thanks for your presentation. Yeah, thanks for your time. Let me know if you need me. I can add some links to the video description. And if you have a post to share about your hiring and internships, we can share it on Zero Exponent's Twitter.
Sure. So I hope, Sylvia, if you're watching, yeah, please.
Yeah, we'll be in touch.
Yeah. Cool. Thank you guys for listening.
Yeah, Rikard, thank you very much. See you soon.